We present our work, Learning Human-Aware Robot Policies for Adaptive Assistance. Our work deals with assistive robotics tasks, such as feeding, bed bathing, and drinking. Here we display our method's successful cases in these tasks. Our task scenario is demonstrated with the feeding example in the figure. The initial objective of the robot and the human is to achieve the basic goal of feeding the food, represented by the task reward. However, in real-world scenarios, humans often have individual preferences, such as preferring the robot to be gentler during feeding. Such preference satisfaction is represented by preference reward, to which robots typically lack direct access. This misalignment between the human and robot reward functions poses great challenges in robot assistance. To address this misalignment, we seek to answer two critical types of questions in assistive robotics. In the feeding task, if a robot could figure out questions like, where would the user go next, in the motion anticipation level, and, should I feed more gently, in the utility inference level, it can recognize the individual preferences of different users, providing more adaptive assistance. Here is the framework of our method. The human agent is controlled by an independent reinforcement learning policy, with visibility to both task reward and preference reward. Due to the requirements of real-world assistive settings, the robot agent, which is also controlled by a reinforcement learning policy, can only access task reward. Moreover, to address the critical needs of human motion anticipation and utility inference, we propose two key modules, respectively, the anticipation module and the utility module. The anticipation module is designed to model human behavior and predict future human motion. By using this predictive information to guide robot policies, the robot can deliver assistance that align better with human motion trends, enhancing task performance and reducing discomfort. The utility module enables the robot agent to infer a human's utility function that reflects individual human preferences. Specifically, this module aims to estimate the weights of different human preference items in a given preference settings. The preference weight distribution can be obtained from expert demonstrations through a sampling process. For more information, please refer to our paper. We first present the performance comparison result, using robot Sawyer in the feeding task under multiple human preference settings. In Table 1 on the left, our method demonstrates superior performance in metrics such as human reward, penalty values of individual human preferences, and task success rate. The training curve on the right also shows consistently higher reward values throughout the training process. Our method enables the learnt policy to be adaptive to individual human preferences. For example, in the setting where the human prefers gentler delivering forces, our method produces slower and gentler delivery, whereas the baseline methods fails to do so, as the spoon is moving too fast when approaching the mouth. In the setting where the human prefers the robot to avoid spilling food, our learnt policy effectively recognizes and adapts to this preference. In contrast, in baseline policies, food are spilled midway, making both the preference reward and the task reward suboptimal. Furthermore, we present the comparison results for different assistive tasks using robot Sawyer. For example, in the bed bathing environment, a person lies on a bed in a random resting position, while a robot uses a washcloth to wipe off uniformly distributed water markers on the person's right arm. Our method efficiently and effectively completes this task. In contrast, with the baseline methods, the effective contact between the robot end effector and the arm is significantly reduced. In the drinking environment, where a robot holds a cup of small particles representing water and helps a person drink them, our method also completes the task efficiently and effectively. In contrast, the PPO baseline methods produces less effective coordination policies. In the TD3 baseline, the robot end effector even gets stuck midway. Finally, we present the comparison results. With different robots conducting the feeding tasks, our method delivers generally superior performance across all robot environments. For example, with the Jocko robot, our method yields a clean delivery, while the baseline methods produce suboptimal policies, in which the spoon hit other facial parts. With the PR2 robot, our method also yields a clean delivery and avoided spilling food. In contrast, in the PPO baseline, the food spilled out almost entirely. In the TD3 baseline, the spoon stuck midway, making task success impossible. With the Baxter robot, our method yields superior performance in terms of delivery cleanness and gentleness. In contrast, in the PPO baseline, the spoon hit other facial parts, and in the TD3 baseline, the delivery was less gentler, making the preference reward suboptimal. These presented results demonstrate that our method is superior to previous baselines in terms of task success and adaptability to human preferences. Thanks for watching.